Hello, I'm Nicholas Luciano.
And I'm Gabriella Pangilinan, and we're from Swarthmore College. This is our project for the 2018 Amalthea REU Learning to See, an adaptive model for tagging complex scenes.
Current computer vision algorithms and convolutional neural networks are highly accurate in detecting and classifying objects in standard videos. However, more complex video scenes present abnormalities that are challenging for standard classification methods. In this project, we explore how intensive preprocessing techniques affect the ability of deep learning-based methods to detect and accurately identify objects in video frames in real time.
Our system is an all-in-one model for detection and classification, which incorporates denoising, background subtraction, foreground extraction, and object detection to improve classification. The steps allow a greater number of objects to be detected and classified in a given video frame. As the diagram shows, we take an input video frame by frame, pass it through our tagging system, and the system outputs video frames with tagged labels.
The first step of our model is noise removal. We use a denoising convolutional neural network which, unlike other noise removal methods, can reduce noise in videos with an unknown noise level. The picture on the left is an example of an incorrectly classified object from a noisy frame passed directly into a classification algorithm. On the right, the classification algorithm is able to correctly tag the object after the frame has been denoised.
The next step in the system is background subtraction. When a video has moving objects that are far away, we want to extract these foreground objects and pass them directly into the classification algorithm. We use two methods to subtract the background from these frames, the Kalman filter and the Gaussian mixture model. However, both have separate disadvantages, so we combine their results into a unified model for more accurate estimation.
The final step of our model is classification. We use two different classifiers, a single-shot multi-box dissector and Inception v3. SSD is used for detecting multiple large objects in the foreground and is trained on broad categories of objects. Inception v3 is used for smaller objects that SSD misses and is fine-tuned to detect specific types of objects.
An important element of our system is that it is modular. Depending on the specific characteristics of a given video, it might not need to go through every step of our system. For example, a video with a static camera, static background, and only a few objects of interest will be easily tagged by SSD. Denoising and background subtraction may not be needed. However, the classification of videos with a dynamic camera, dynamic background, and multiple objects may be improved by subtracting the background to detect foreground objects.
Our system can be applied in settings where information is extracted from videos that need manual review. For example, marine biologists review underwater video to track fish populations and monitor invasive species. In agriculture, farmers use drones to capture GPS maps of their fields to help plan where to plant their crops. The videos in both of these settings are difficult for standard classification methods, so our system would be helpful in making these processes autonomous.
We'd like to thank the ICE Lab, FIT, and the NSF for this research opportunity. Thank you for watching.